with Professor Anto from University of US Federal Training. The title of topic is volume eigenvalue in most major metric space.
So first, I thank the organizer. This is the first trip to Taiwan. Even we have learned a lot when we were charged about Taiwan. So I think I forgot to put a word in the title. The volume and estimate on smooth magical measure space. So today I will talk about the volume, and tomorrow I will talk about estimate eigenvalue. So when we first look at the gradient shrink-rich solid, So later I will just call it GSRS. So usually I just normalize it. So Ricci F equals to Ricci. With the 1/2, and in this case we have just put the information here, so we can normalize it as this. I was interested in this when the first time I met I talked with Huaidong said to me, I think maybe more than 10 years ago, Huaidong said the Ricci shrinker is more or less, it has some similarity with a positive curvature manifold. Yeah. So we start to think about some basic properties, basic theorems in Riemannian geometry. First one is Bonnet-Mills. Which said if the Ricci curvature is bigger than or equal to the Ricci curvature of sphere, then the diameter is less than or equal to the diameter of sphere, and the fundamental form is finite. And the second one is volume comparison theorem. Which usually we call Bischoff-Gromov. Yeah. Bischoff-Gromov theorem. So we can ask a lot of questions. Another one is Nishanovich-Obata theorem. Obata. So of course we can continue asking some questions, but even today I think the problem is not totally solved, because for example the Bonnet-Mills theorem, of course you have non-compact ones. We usually model as Rn or cylinder, so diameter can be infinite. But if it is compact, can you estimate diameter? So also the first and fundamental form is finite. It's not very difficult to prove. And about the volume comparison theorem, the Bischoff theorem, for example, you can look at the comparison theorem. You compare with of course you have two kinds of volume: F volume or the remaining volume. So of course, we have some estimate for volume, but we still don't have a sharp estimate. That means when you have volume of the ball less than or equal to volume of Euclidean space, then equal holds if and only if it is Euclidean space. For example, we don't know yet. Maybe I'll try to give an observation about this. And maybe this kind of, the first eigenvalue of, if the Ricci curvature of the manifold is bigger than, or the Ricci curvature of sphere, then the first eigenvalue of the Laplacian is bigger than or equal to the first eigenvalue of Laplacian of sphere. And the equality holds if and only if it is a standard sphere. So the most, maybe this case, we have a satisfactory, I have to speak English for a long time. So answer. That means if Ricci f is bigger than or the Ricci of the Gaussian soliton, then the first eigenvalue of Laplacian f, drifted Laplacian, is bigger than of the first eigenvalue of cylinder. And the equal to the holes if and only if is a cylinder. So this case is more or less done. So I will continue to talk about this tomorrow, related to minimal hypersurfaces. So today I will talk about this kind of stuff, and then if I have time, maybe I give some consequences of this kind of result. Okay. The result can be generalized to some case like this. So I will have these conditions. So these conditions implies R2, and then it implies, so this is, in this way we have minus f equals to n over 2. So usually we can, this implies, because r is bigger than or equal to 0 by chain, so we always have gradient f squared minus less than or equal to r. So this condition can be generalized, the bigger than or equal to g. And also this one can be generalized to less than or equal to k. So we can use this kind of stuff, and we will see actually it makes sense when we use these conditions. So let me start with a theorem we proved with Huaidong in 2010. So for the for the normalized Ricci soliton, we have of course, from this we immediately have this one, the distance function plus, and on the other hand we have C1. From this we know that where C is a constant, we know that this has a behavior just like a distant function. So this leads us to take this function just as a function we used to as distant function. So we can use this to prove that the volume of bore is less than or equal to C2R, and where C1, C2 depend on the geometry of the unit bore. In the work, we didn't care a lot about how it depends. We also didn't know the sharp constant of C1 and C2. So what is the best constant for this? Let's check. So it is almost 1 year later, so there are two, Hasselhofer and Müller, pointed that if the P is the minimum point of the function f, then he can choose the C1 and the C2 only depend on n. But the constant is not sharp, which I'm expecting that if you have this kind of estimate and the equality holds if and only if it's a Gaussian solid. Okay, so let me state a result like this. We can do the estimate on this side, and we will have estimate for this kind of estimate with C1 only depend on P for any P. P is not necessarily minimum of the F. Actually, this theorem, this is a joint work with Shen. So more precisely, it's as following: if Ricci F bigger than or equal to 1/2, and I will take this condition. So if gradient F square less than or equal to alpha square f for some constant. So then we can write this constant for any p n. So the fx alpha is bigger than or equal to 1/2 the distant function minus a constant to n. I can write down the constant. 6 minus 2 plus alpha. So combine this, we can, we can use a lemma, which proved by Ovidio Monteano. And Jiaping 1. It's the following. So if you have a geodesic, if you have with Ricci F bigger than or equal to 1/2, gradient F squared less than F, then if the conjugate radius equals to 2r, this implies that 2fq for any theta q theta in a unit bundle. So this less than or equal to 2. To R. Where gamma is the geodesic from Q in the direction of theta. So from this, we have a corollary. If for grad and Ricci soliton, just for simplicity, the conjugate radius equals to 2. If it's equal to 2, then the diameter is less than or equal to 20. Of course, this constant is not sharp. Minus 20 plus n. So the question is that actually we can give the estimate using the conjugate radius. But even it's not sharp, the estimate is useful in some questions. From the history, we know that we get estimate because of the hint of this function. But a few years later, Ovidio and Japin discovered that actually the estimate can be obtained by these two conditions. And the way is very classical. It's just used in the beginning of the proof of Bischoff-Gromov with some clever tricks. So so totally, for the volume estimate, we have 3 different proofs. The first one is the one given in the paper. We use this one as a function rho, and since this function is asymptotically as the distant function, we only need to see the level set of this function. And the second one is it has some independent interest. Is that we have 3 conditions here. These 2 conditions also implies volume estimate. Even we don't need this one. We have volume estimate for the level set of F, which makes sense for self-shrinkers. Actually, you don't need this. If you take a submanifold in Rn, you just take a distant function of Rn, it restrict to the submanifold. So this function usually is does not have a symptotic behavior like this one. But it makes sense you estimate the extrinsic volume of the submanifold. So this first proof, and I will spend some time a little bit about another 2 different proofs. So I will put the theorem here, which is also Christian. That means we have this condition. We have this. This is 1, 2, 3. So assume 2 and 3. And we define a dr is just x with 2 less than r. This implies that we have volume of f n, which is defined as E minus f dv n, which is finite. And we have volume of dr less than or equal to a constant, which only depends on volume f n r to k. So it implies that you can, if you take this function f to remarks, if which is bigger than or equal to 0, you can take f as r squared over 4. Then you have the Laplacian theorem. It implies you have 3. So you can recover the classical Bishop-Gromov theorem in this case. And the second one, if you take f as, if m is k r, a self-shrinker, I will not explain, maybe I will explain the next time, then you have volume estimate. It implies that m intercept for r, the extrinsic volume less than or equal to r, the dimension is n, where C is only dependent on the entropy of the manifold, of the submanifold. Also, if this, I have another small remark. If the scalar curvature is bigger than or equal to some constant, let's say R0, so you have a better estimate volume of ball less than or equal to C R 2n plus n minus 2R0. So you have a better estimate in the order here. The proof is this one? Diameter. So I would like very much to say a little bit the Montiano one's estimate. Actually, first his result is 1, 2. Yeah. 1, 2 implies the volume of the bore constant or depend on n. E is P R N. Yeah, I have thought a lot why this happened. For example, if we have a scalar curvature bigger than a constant positive, from this one we get a better estimate in the order here. But if you use this estimate, you cannot improve this one. For example, you take the example of the cylinder. If you have a cylinder, you can. I mean, one should have a theorem to generalize both this estimate or imply this two estimate. But at this moment, I don't have. I think essentially the same proof implies that for gradient shrink rich soliton, the estimate can be like this: the volume of BP R less than equal to E minus R0. No, not R. Volume of ball. The advantage is that advantage of the Montaigne 1's proof result is for NP here. So of course, for gradient rich soliton, where R0 is the infimum of the scalar curvature, and equality holds if and only if this is Gaussian soliton. So they proved the rigidity. Of course, it's interesting to find some estimate to, for example, as I mentioned in the beginning, for this kind of case, the first eigenvalue can characterize all the cylinders. But in this kind, I was hoping maybe there is some kind of estimate such that you have this kind of rigidity for cylinders. Okay. Any question? So I will compare two proofs. Maybe we can understand better why we still don't have the combined results. So the proof of this is quite simple. You just take the proof. This is the proof 1. I just proof of theorem 2. It's a theorem 3. It's quite simple. You just define a function R T K dr E F. If once you have this function, the proof is quite simple. So 3 implies that I prime t less than equal to 0. So that means that you have I r squared less than or equal to 1 when r bigger than 1. So in this, excuse me, it's minus. So you have r minus 2k dr e f over r squared less than equal to 1. 1 is this 1, and then this 1 is d of r e minus f. So this one is bigger than or equal to a constant 1 over 4 r minus 2k. At the volume of dr. This is weighted volume. This implies that the weighted volume is finite. So you have this volume less than or equal to so this implies the estimate. The proof is quite surprising that you just using you're beginning with the standard proof of the Bishop-Gromov. You just write the volume form of R theta, dr d theta. Then you have if you define omega r theta log j. I just write down to see why the rigidity comes in square. Which along each geodesic, you have this one less than or equal to 0. When equally the holes, if and only if the sphere is totally umbilic. So I will not do the detailed computation here. Just write the estimate here. So you just put this r squared omega less than or equal to minus 0 r omega s squared. So you can drop it. This is less than or equal to 0. So you finally you will have n minus 1 r log j of r apply is equal to minus s. So now you can use this one. This is equal to less than or equal to 1/2 to apply. So finally, you will have the terms this less than or equal to minus R0 plus Fp. And equality holds if and only if F equals to S squared over 4. So you can calculate equalities all these steps. So when you have this one, quickly you have this estimate, then you have the rigidity. Actually, they proved this, even they didn't say that explicitly. Maybe you guys knows before. By developing this idea, we can get some more estimate for volume. For example, we can have this kind of theorem. If Ricci, this is one, Ricci F bigger than or equal to 1/2. If F of X less than or equal to some kind of A2 D squared D2 D. This is a D of this distant function C2 bigger than or equal to A1 D2 squared B1 B C. If you have this, you still have volume of B P of R is less than or equal to the constant, a constant, then E A2 this R squared some B2 plus B1 R plus some constant here. You still have, of course, this estimate is far from sharp, but you have this estimate. It is useful for in some cases, and a remark is that still Ovidio and Japin proved that actually this one implies Ricci F bigger than or equal to 1/2. Implies that A1 can be chosen to be 1/4. When the manifold is not compact. So if you come back, we come back with the estimates here. That means A1, A2 is, in this case, A1, A2 is equal. This is 0. So you have estimate more or less the polynomial growth. Actually, the motivation I do the estimate is to consider the variation formula of the entropy in the case of in the non-compact case. The variation formula has in the compact case has been done by Huaidong, Tom Yilma, E. Hamilton, and then for the Ricci soliton case also done by Huaidong and Mengzhu. So during the proof, we will need this. Actually, it's a general question for the manifold, the question is like this. When a function h equals to 0 for some h positive. In our case, we are interested when h equals e minus f. So when this happens, Laplacian e minus f, which is equal to Laplace f e minus f. In the shrinking soliton case, it's equal to 0. So if you take a perturb of the shrink soliton, this one guarantees this one is also 0. Then that means that a corollary is that Ricci f is bigger than or equal to 0 if f divided by distant function is bigger than or equal to a1, less than or equal to a2. If a1, a2, a1 less than or equal to 1 over epsilon 0, square. So we have so we can go through the proof to compute the first and the second variation for W function, not the new functional. You have the new functional one. So, of course, I didn't have enough time to prepare the transparency. I just stop here. Thank you very much.